What's up, mathematicians? Welcome back to our lesson number 4 on conditionals. Now, in the last video, we looked at different forms of conditionals, and in this video, we will be looking at something called the biconditional and the concept of logical equivalence. Okay, so before we get into that, I mentioned in the last video that I don't want to spend too much time talking about this idea of truth as it relates to conditional statements. But right now, I do want to take a few minutes to consider this idea of truth. And to do that, let's take a look at one of our conditionals from the last video. So here we go. This conditional statement, if you live in LA, then you live in California. It's pretty clear, and as we discussed in the last video, that the original conditional and the contrapositive are both true. And in addition to that, the inverse and the converse are not true. But now let's look at that other example that we talked about in the last video. If you're bookish, then you like books. And the converse of that, if you like books, then you're bookish. How would we know if these statements are true, if these conditionals are true? It's a little bit less clear, and it really comes down to understanding the definition of the word bookish, right? So what we need to do is try to understand the meaning of this word. If you're trying to determine truth, definitions, it turns out, are really important. So once we really understand the meaning of this word, we can try and determine, is it possible for a bookish person to not like books? And also, is it possible for someone who likes books to not be bookish? In order to get a sense for this, let's take a look at some definitions of the word bookish. So the first thing that comes up in Google is that bookish, as it relates to a person or way of life, means devoted to reading and studying rather than worldly interests. Okay, so that's one definition. Then we come down here and we see Merriam-Webster says, fond of books and reading. So that means, well, if you like books, then I guess you're bookish, according to this definition. And, there's other varieties as well. We go down here, given or devoted to reading or study. And finally, the last one that I wanted to highlight is this one right here. Someone who's bookish spends a lot of time reading serious books. Okay, so having looked at those definitions, I would be inclined to say that if you're bookish, I can't really see how you wouldn't like books. However, I could imagine that someone could like books and not be at the level of bookish. If you went with the definition that bookish just means fond of books, then maybe the converse is true as well. But based on my sense of the definitions, I would say that the conditional and the contrapositive are true, and the inverse and the converse are not true. However, what if both the terms bookish and liking books were actually the same? What if bookish just meant to like books, to be fond of books, as one of those definitions said? So if it turns out that being bookish and liking books are actually the same thing, then we have something called a biconditional. So let's look at how we might write that. So here's the biconditional. It says, you're bookish if and only if you like books. Now, because this if and only if takes a little bit of space to write, typically I'll be abbreviating it like this with this IFF. So this should be read as you're bookish if and only if you like books. Another way that this can be written is with this double arrow equivalence. So you're bookish implies that you like books, and you like books implies that you're bookish. This double arrow means both of these imply the other. So the two parts of a biconditional are logically equivalent if the biconditional is true. So let's look at another example of a biconditional. So here we go. This one says that you live in LA if and only if you live in California's largest city. Now, this is a true biconditional because LA is California's largest city. So if you live in LA, then you live in California's largest city. And if you live in California's largest city, you live in LA. And we could write the biconditional like this. So as I said already, if a biconditional is true, it means that the two parts are logically equivalent. And we could even say it this way, that a biconditional is true if and only if the two parts of the biconditional are logically equivalent. Let's take a little bit of a closer look at that for this particular statement. So consider that this means that the first part implies the second part, and the second part implies the first part, which means that the inverse and the converse are true along with the conditional and the contrapositive. So here we can see that the original conditional could be written as, if you live in LA, then you live in California's largest city. If you live in California's largest city, then if you don't live in California's largest city, then you don't live in LA. That's the contrapositive, also true. And we know these two have the same truth value. But now if we look at the next one, if you don't live in LA, then you don't live in California's largest city. And we know that's true as well. And finally, the converse, if you live in California's largest city, then you live in LA. So we can see that in the case of a biconditional, where the two parts of the biconditional are logically equivalent, all of these have the same truth value. So typically, when we look at real-world examples, like the one we just saw, it'll feel like there are two ways of saying exactly the same thing, right? So saying LA is just another way of saying California's largest city. So what's the point? I mean, it's like saying, if you live in LA, then you live in the city of angels. Or just saying, if you live in LA, then you live in LA. Duh. However, when it comes to mathematical propositions and theorems, things can get a bit more subtle. An example of this is that the Pythagorean theorem is logically equivalent to the fact that similar triangles have proportional sides. We can write this as a biconditional, as you see right here. The Pythagorean theorem is true if and only if similar triangles have proportional sides. Okay, so if you recall, we used the fact that similar triangles have proportional sides to prove the Pythagorean theorem. But it turns out, if we assumed the Pythagorean theorem, we could have proven the fact that similar triangles have proportional sides. This might seem a little bit surprising because these two things feel different, right? So over here we have the fact that similar triangles have corresponding sides proportional, and over here we have this idea that in a right triangle, if with legs with sides a, b, and c, where c is the hypotenuse, a squared plus b squared equals c squared. Okay, so this one is about a right triangle. This one could be about non-right triangles, and there are two of them. So they feel like two different things, but logically they are equivalent. That means that if this is true, then this and everything that follows from this must be true. And if this is true, if the Pythagorean theorem is true, then this and everything that follows from this must also be true. This idea of logical equivalence will be important in the next unit, where we'll use this idea to prove that different propositions are logically equivalent. Now, to do this, we must prove both directions of implication. A famous example is what you see right here, the isosceles triangle theorem and its converse. So what this is saying is that if you have an isosceles triangle, a triangle with two sides equal, then the angles opposite those two sides must also be equal. And if you have a triangle with two angles equal, then the sides opposite those two angles must also be equal. This one implies this one, and this one implies this one. Now, in order to prove this logical equivalence, you have to prove that given this, this must be true, and given this, this must be true. Okay, so we'll get to that in the next unit. So before we go, getting back to this idea of truth, I wanted to close with this example of a biconditional. Okay, so a conditional is true if and only if the first part of the conditional implies the second part. So go ahead and think about that for a few minutes. And that will wrap up this video. In the next video, we'll look at how we can use Venn diagrams to better understand conditionals. As always, thank you so much for watching. If you learned something here, please like and subscribe, and I'll see you in the next video. Bye-bye.